All right, so this is part 2 of our discussion and series of questions on Eulers Method and slope fields. And we did discuss that pretty much most years is one multiple choice question for each of those subtopics, and I certainly wouldn't waste too much time on it. Mr. Rezik, how do you say, is it Rezik?
No, it's Resk.
Resk.
Yeah.
There you go, glad I asked.
Yeah.
Mr. Resk has shown us the calculator, and you do not have to create a program or anything like that. And from memory, how you would do that to do this, you can go ahead and watch part 1, and you can watch maybe the last 5 or 6 minutes of that video. But can someone tell me, who's not Luke Resk, how I go ahead and find Euler's function? The book.
You don't even need to do that. You just go E-U-L-E-R.
You could type in Euler, or the book. Where's the book? Oh, that thing?
Yep.
Okay. Oh, okay. So you scroll down to E, or you could just type E, and it's that function there. Now, as it says, it tells you about it, and we went through that yesterday, so we're not going to go through it again. But I will leave it just there, just for the time being, because I'm going to go through a slope field question. Now, I asked you not to really have a go at the slope field questions because I'm going to explain how I do them, and I guess we I can say that it's a waste of time doing them in your calculator, because by the time you put it into your calculator and there are some limitations to doing that, just wouldn't bother, because I'm going to talk to you about how I eliminate and sometimes just find the answer virtually straight away. Now, first of all, what can you tell me about x and y? Like, if I go across values of x, can they change? Is this thing the same as this thing? Y values. What about here? Okay, you notice it's changing. So as as x changes, then the slope does change. So it definitely contains x in it. And it definitely contains y in it as well, because as we go up y's, you can see here that the slope's here and this slope is different to that slope. That's always the first thing you do, okay? Now, let's sort of think about some things. Let's pick, this is dy dx equals x squared minus y squared. Let's pick a value, like let's pick a really high x value, okay? Really high x value, say over here, and a really low y value. Now, or let's say a value over here. Now, if I pick sort of the same value, then you probably will notice that x squared minus y squared, I don't think that's really going, like it's got a slope there. If I've sort of got a similar sort of x and y coordinate, that's going to definitely not be a very big slope, is it? So, you know, I ruled that out. Similarly, if I did the same thing, then that's going to rule that out. Okay? Now let's pick some values. The thing is, you haven't been given any specific values, but what can you tell me about the slope? What can you tell me about the slope at x equals 0? What is dy dx looking at that slope? It's 0. So doesn't that mean that if at x equals 0, wouldn't the slope be undefined there for that? Correct? Okay, can't be that then. So suddenly we're looking at 2 options. Now, let's pick a value. Let's pick a positive value. Now this is when you start going, I'm going to look in the first quadrant. Okay, you don't have to. Okay, let's have a look in the first quadrant. What can you tell me about all the slopes in the first quadrant? They're positive. What can you tell me about x values and y values in the first quadrant? They're positive. So a positive divided by a positive is a positive. So what's the answer? E. Okay. Now, can I just say this? I think that the easiest way, there are some ones which are tricky when like to determine whether it's got x and y in it, you have to have a look with changing values of x. Are the slopes changing? Yes, they are. With changing values of y, are the slopes changing? Yes, they are. It means that the derivative function, this differential equation, can be approximated using this function. The quadrants, I believe, looking at quadrant 1 is probably the easiest way to do this question, but it just depends on the question, so we're going to keep going. Now, as we go through them, you're going to eventually realise how quick they are. Euler's formula is used to find this and yada, yada, yada. Now, let's go to our Eulers, yes? And someone's going to explain to me how to do that question. Is anyone willing to put their hand up and have a crack? Is anyone willing to have a go at this in the calculator?
I'll do it.
You'll do it? Okay, good. Thank you. Thanks, Dan. Beautiful.
All right.
All right, so Dan's going to have a go, of course. Now, he's got the exam question up, so
Yeah.
good.
So first you enter in
So we've entered the Euler thing, good. So
that,
pause.
the derivative,
Good. So he's entered the dy dx equals.
and then you do comma x, comma y,
Good.
and then it's comma, and then you set I guess it's like the domain of the x value for what you want.
Yep.
So from x0 to x2, and x2 is 0.2,
Good.
and then comma, and then you put in y0, and then your h value, and then the answer is the bottom right corner.
Beautiful. Because you can see that the step 1, step 2, so step 1, step 2. Very good. Is that presented us with an answer?
No.
Okay. Now, let's have a look. Let's have a look at what we've got. So that's where we have to know how the calculator thinks. Now, the thing is that the value of y2 correct to 4 decimal places is... Okay, what's happened?
We've got B or C.
What's that?
We've got B or C.
We've got B or C, is that right? Okay, so that's where, yep, well done, Daniel. You know that you've ruled out everything else, yes? You okay with that? Now, how do we find... Now, is it an underestimate or an overestimate? Ben?
What I would do is I would look at the derivative of the derivative and
Okay.
see how the gradient is changing at that point in time.
Okay, good.
So because it's like a linear approximation,
Yep.
it will give you like a tangent,
Mhm.
and then you'd look at where the actual graph would be at that point.
Good.
So like if the actual graph was increasing, then the approximation would be like
So
under
we're
it.
talking about the derivative of cos x,
Yeah.
which is minus sin x, is that right?
Yeah.
So what does a minus sin x graph look like at where we were looking at it at what?
X is
equals-
0.2. It will be a negative.
Yep.
So it's actually decreasing. So
Yep.
the estimate will be over, I think.
Do you agree with that?
Makes sense. I don't know if it's right.
So it's an overestimate?
Yeah.
I agree with that. Well done. Well done. Very good. Well done.
was
Yep.
just going to say, you could also just like actually, like because this is a calculator one,
Yep.
we could technically just use the calculator to find out what the antiderivative of cos x is at
Yep.
0, 1, and then just put in 0.2 as the x value and then see what that number is.
That's right. Fantastic. Well done. Well done. That was brilliant. Excellent. Answer is correct, B. Okay, so we've gone to an Euler. Now remember, 2012, I'm putting the stuff that was on in recent years' time. Guess what? Question 9, Eulers. Question 10, slope field. It's basically like this all the time. So let's go back to this. Now, have a look at this. dy dx equals xy. Now, what method are you going to do for doing this? I think quadrants. Okay? First quadrant, positive and positive, yes? Okay, we've got a positive x and we've got a positive y. Positive x and a positive y. Let's have a look. Are they all positive? Yep, okay, they're positive. All right, what about over here? Ooh, what about this one? Are they all positive? C's wrong. What about if I had x, y, and I had a big value and a big value? Yeah, it certainly could be D. Could it be? All right, so have we only just ruled one out? What's that? It can't be. Why can't it be B?
Yeah, why can't it be B? Oh, well, no, we're not looking at that yet.
All right, let's do this then. Let's do the third quadrant. Let's have a look at the third quadrant. What is a negative times a negative? Positive. So, what can you tell me? Is this one positive? No. Get out of here, man. All right. Is this one all positive? It could be A. What about this one? Could be. Okay. What about this one? Yeah, it's positive. It could be. All right. Okay, so we've ruled out 2. Let's just try. Are there any which... Let's look at the second quadrant. Okay, the second quadrant means that it's going to be a negative value of x, a positive value of y, which is going to be negative. Are they all negative? The ones that are left? Okay. What about this? Let's pick a point. Let's pick a point at 1, 1. What's going to be the gradient? 1, 1. It's going to be 1, isn't it? Okay. Now, at 1, 1, is this here? Oh, actually, we've already crossed that out, haven't we? All right. So that looks like a 1, 1. What about this one? That looks like a 1, 1. What about like? Oh, so. You know, this one is not the easiest of ones to get. But has anyone got any suggestions? What?
Either A, put it in the calculator, or B,
Yep.
pick a higher value of x times y.
Yes.
So that means on that line of y equals x,
Mm-hmm.
you can rule out B because x times y at, for example, x is negative, at x is 4, y is 4.
Yep.
Is not going to be 1.
Yep. What about this though? What about at x equals 0? What does y equal? What does the derivative equal? 0. Do you see a straight line there? Do you see straight lines there? I reckon maybe it's not even E. What do you think? Okay, I've ruled those out. Now, we've got 2 options. 2 options. What do we do? What's that? All right. Well, the thing is that the gradient on the axis is 0. We know that, and for both of them, that is the case. But what about negative gradients in the second quadrant?
Yeah, they're all negative.
They're all negative?
Yeah.
Yeah, but what about the size of the gradients? They're what they should be? Well, let's pick out 2. Let's pick out 2 and let's pick out negative 2 and 2. Okay, let's pick out negative 2 and 2. If I had negative 2 and 2, does that gradient look like negative 4? Nah. Negative 4 is quite big, yeah? Like it's quite like almost straight. If you ask me, then rather than that gradient, you want some pretty... So negative 2 and 2, virtually like a straight line, if that makes sense. So that's where you have to look at the gradients. Now remember, we looked at if I had one here, if I had one here and I had one there, then of course, then my gradient's going to be like that. Well, if I had for every one it goes up 4, let's say 1, 2, 3, 4's up here. I'm just going to do this, okay? Then my gradient is going to look like that. It's going to be pretty high. It's going to be like almost a vertical line, not quite. So can you see here there that point at negative 2, that was not an easy question. Not one of the easier ones. So the answer there is A. All right, now let's do them. This differential equation is best represented by... Now, first of all, do they all have y's and x in them? Yes, they do, so there's no point there. If we looked at quadrants, it might be an idea. What do you notice? What do you notice about the gradient at x equals 0, though?
It's constant.
It's constant. Okay. Now, if it's constant, then that means that we've got, like, if I had this over this, okay, if I had y over 2y, then that's a half. Does that gradient look like a half? It could. If I did this...
It can't be because it's negative.
What's that?
It can't be because it's a negative gradient.
It's a negative gradient, x equals 0.
Yeah, so it can't be A.
Can it be A?
No.
Can't be A. Okay. All right. So what else can we do? I don't know if I agree with that. It can be A. Well, because I'm crossing out that because x equals 0. I'm crossing out that because x equals 0. Y on...
Y equals 0.
Yeah. Okay. Y on 2i. I'm actually going to say that this gradient of a half, that could be a half. Let's try x equals 0 here. X equals 0 here. Is the gradient negative? Nah. X equals 0, x equals 0. Is the gradient 2 though? Oh, it doesn't look like it. X equals 0. Now it could be that one, couldn't it?
It could.
So I can't rule it out. X equals 0, x equals 0. Is it negative?
Nah.
There you go. So if you're having a guess, you're not guessing A to E, you're guessing A or D. That's a 50% chance. That's why you can still ace the exam. If you ace the extended response section and you had 3 multiple choice questions, then you've actually got 2 to the power of 3 chance, which is like 8. There's 8. 1 out of 8 chance. If you had 3 questions you're unsure of, if there's only 2 options that are viable, you have a 1 out of 8 chance of guessing those 3 questions and still getting your full marks. Okay? That's why in exams, with those questions, you cross them out, don't you? All right, so I'm going to pause the video. I'm going to have a little discussion here as to what do we do here to actually work out which one it is. It's A or D. Okay, so can you just explain, Dean, what your understanding was, why it's A or D? Which one is it, by the way?
I said it's A
Yep.
because we said at the start that on the x-axis it's constant gradient.
Correct.
So that means that y equals 0, the gradient has to be negative.
Yep.
And if we were to make y equals 0 for D,
Yep.
then we'd have negative 2x over negative
So
x.
what I might just do is just get rid of... Ooh, there you go. So continue.
Yep. So if we made y equals 0 for D, it would
Yep.
be negative 2x over negative x, and that's a positive gradient. So
Okay,
it's
so
not,
it's not
D.
D.
No.
Good work. So you know you're not walking out of that exam going, I'm not sure. You've just ruled out all the options, yeah? A lot of the time, these questions might take you the full 1.5 minutes. Okay, but as you get better at them, you'll do them in less time. All right, now, I think it's about time. I guess let's skip that. I'm not going to do another Eulers because we can do those later on in the year. And I don't want this video to go forever, but let's have a look at this slope field. Okay, what about this? According to this model, for k is greater than 0, v dt is equal to. Now, let's have a look at the gradients. What do you know about the gradients? Are they negative or like 0? Yes. So what can we rule out, do you think? We can D definitely, because k is a positive constant. And E? B. Okay. Good. All right. What else can we do? Yes, Ben.
When v is 0, it appears to not exist.
When v is 0,
Yeah, it looks like there's nothing there, but I'm not too sure about that. 'Cause it might just be like, just the way it's printed.
okay, sure. So I think that, yeah, what he's saying is that v equals 0 doesn't look as though there's a... Yeah. And at but at t equals 0, v does... Now what about here? T equals 0, do you notice that these gradients are changing? Okay, so at t equals 0, then can't that rule that one out? Yes, it can. We've got two options. Which one is it? The answer is C. And why is the answer C, and why can't it be E?
Because if v becomes greater.
Just wait. You can explain, Luke. Resk. Oh, sorry, mate.
So because as v increases, the gradient also must decrease. Becomes steeper and steeper. But in E, when v increases, the gradient actually becomes smaller, but closer towards 0.
Yeah.
While in C, as v is approaching infinity, negative kv squared is also approaching negative infinity, which is seen as you're going up the graph.
Good.
So it has to be C.
Excellent. Well done, guys. That's great. And thanks again, Luke. So we definitely cross this one out because greater values of v are going to be smaller gradients as well. Okay? Smaller gradients are not going to be really like high. Okay? Incredibly small values. Okay, now, Eulers method, you can do that in your calculator, that's fine. Let's look at another slope field. Now, the thing is, do we ask ourselves, now first of all, you can really tell a lot of this because doesn't it like, look, what sort of shape is this making? An ellipse. Okay, so it's making an ellipsy shape. Okay, so if it's making an ellipse shape, then, you know, which one of these might not be an ellipse?
No, yeah, they're not derivative functions for ellipses. They're the actual function for an ellipse.
That's right, exactly. These, exactly. Now, the gradients are forming what looks like an ellipse, but that doesn't mean that it's an ellipse function itself, yes? Okay, so instantly, which one do we cross out? A and? And E. Okay, good. So we know the answer is B, C, or D. I'm going to test. I'm going to do a little test here. I'm going to say when x equals 1, y equals, and x equals 1, y equals 1, shouldn't the gradient be, the gradient is what? It's negative. So I'm going to test that out on here. X equals 1, that's 5. And that's going to be negative. So could it be B? Yes. Could it be C though? So it's negative. No, so it can't be there. Could it be D? At x equals 1, y equals 1. I've picked a point, haven't I? Because at x equals 1, y equals 1, dy dx there would be equal to 5 over 16, which is positive. And we do know that at that point that is a negative gradient. There you go. I've picked a point. Answer has to be B, doesn't it? Make sense? Good. Good. Yep.
I was just going to say that there's also like another way.
Now, what we did say is that there are occasions, a lot of the time, we look at quadrants. Now, the problem is that the problem with putting it in the calculator is if you've got 2 or 3 things to pick from, it takes a fair while to put it in your calculator and check them. I'm tired too, Jordan. I know what you mean. Now, what's happening here as y values change, does the derivative change at all? No, aren't they all constant? Like as varying, this slope here is the same. They're all the same. So it doesn't even include y in it. So we've got 3 things to put in. Now the thing is that you've got those 2, and you know it's like this. These could be distractors, and some people could say, well, this one, and a lot of the time this is the case, but don't bank me on it. Let's just say that 80% of the time they've got 2 things which are sort of pretty similar. When you've crossed out 2, then let's just pretend to cross that out. Okay? Now I'm not going to say this works all the time, but if you had to under time restrictions, that's just one of those things that VCAR tend to do. So let's just say you've got that. That means you only have to put in 2. Now I've then gone ahead and I've gone to my graph screen and I've graphed this. Okay, now what I've done is I've gone to menu and I've gone to graph type and I've gone to differential equation. And then what that's done is allowed me, the problem is though, is that when you do it a second time, it craps itself. Okay? Because what happens here is it's saying y2 dash, but what's happened? Has the differential equation that we had originally disappeared? No, it hasn't. So there's actually some issues with doing these on a calculator, especially in an exam where I think personally I'm going to maybe pick a point that I know really well, okay, for those 2 things. This is the intuitive way to do it. I'm going to then say that VCAR probably have got 2 things which are similar, so I'm just going to have a guess at those first, and I'm going to try those values. At x equals pi on 2, what does y equal? What does dy dx equal? In this B. Isn't cos of pi is negative, yeah? -1. Is this negative? Here, are all of these negative? Yes, they are. Okay, what about at cos of a half pi on 2? Pi on 4. What is it? Positive. So once again, I've picked a point over here. Cos of pi on 4 is positive. So what's the answer? Thank you. Now, as I said, this is the thing, is that then they give you different scales, ladies and gentlemen. They give you different scales, and the problem is that I've done my slope field on here, and sometimes it's hard to sort of decipher between this and that's why I think it's a bit of a waste of time personally. Okay? And yeah, I'm just telling you, just don't waste your time on it. Don't waste your time on something you don't need to do. That's my honest opinion. All right, now we've done that. I'm going to stop the video here because it's gone for 28 minutes, and we'll be sort of having a bit of a rest soon and a working lesson and things like that, chilling out. So I'm going to stop it there. Are there any questions? Did you have a question, Ben?
Yeah. When you put it into the CAS, and you put in cos 2x, how did you put in cos 2x if you didn't know what it was yet? If that makes sense.
Well, I put in cos 2x as I had to actually pick one value. So because it's one of the options, so I put in cos 2x. And you could even put in some initial conditions. These things here, down here, they're initial conditions. Okay? And if you have initial conditions of your expression, then you can actually go, it actually can trace your solution curve. Now I'm just going to stop that there. Oh, look at this. Oh,